live stream. So that should be coming on in a few seconds. And I'm going to close this tab. So we got a conclusion. This is not for me. Just like those medication commercials. This is not for me. If you use VI and use punctuations a lot, this tool may not be for you. It's one of those. All right. So what we are going to do today is to continue our topic of binary addition. So yesterday we talked about how carry repo adder, is not very efficient because the amount of time for the adder to settle is proportional, linear, to the number of bits, that we are adding. So that means, it will take twice as much time to make a 4-bit for a 4-bit adder to settle down compared to a 2-bit adder. It would take, an 8-bit adder would be twice of the time of a 4-bit adder. A 16-bit adder would be twice the time of an 8-bit adder, and so on. So the design is really elegant. The carry repo adder design is very elegant. And most classes that talk about computer architecture will stop there. It would just go like, okay, now we have a functional adder and we're done with this topic. Well, not here. Okay, so we are going to go forward and talk about carry look-ahead adder. Okay, because carry look-ahead adder is a design that will basically eliminate the whole concept of repo, and as a result, it is a faster way to implement adders. All right, so let me see if I can go back to the module. Yes, I can. Okay, very good. And then what we're going to do is to start with section 6 because we are now done with all of the other sections. So before I move on and start to talk about carry look-ahead adder, I want to see if there are any questions. So it would appear that there are no questions. I think I should probably have a little sound effect thing that can emit the sound of crickets, and then have tumbleweed to go over my capture screen. All right, so algebra. Okay, very good. Okay, so that's good because somebody actually read the note ahead of time. That is great. So I'm gonna let Paul, go ahead and ask the question.
So I guess as I understand it, wherever we see something that looks like multiplication, we should take it to be and wherever we see something that looks like addition, we should take it to be or.
Yes. So within
Okay.
the context of all of these are Boolean expressions, then we have, in the previous class I talked about the shorthand. So when you look at, this xi, yi, it looks like multiplication, but it really is conjunction in this case. And then the plus is disjunction. It also follows the same priority, or same prioritization of operators because we always group multiplication first, and then we perform the addition in normal algebra, and it's the same way here. All
All
right.
right. Thank you.
Yeah, absolutely. Absolutely. Okay, well, I did this because, otherwise I would have to type a lot more operators and potentially use a lot more parentheses. This way it is a lot more concise. And an exclamation point is still negation, and negation has the highest priority. In other words, negation always works on whatever is immediately right after the operator. So in this case, it is the negation only applies to xi. It does not apply to yi. So this is basically the negation of xi and yi not negated. Any other questions? All right. If then, yeah, go ahead. I heard some. Maybe not then. All right. So we'll go ahead and start with the first row. So yes, we are going to go through this derivation, even though it looks really ugly. I do not expect you guys to derive Boolean um, expressions like, not derive, but to use Boolean algebra, like the way I do it here, because that's the content of CISP 440, not CISP 310. However, this is an exposure, okay? Because most of you either have taken CISP 440 already, or you will have to take CISP 440 later. So either way, I think this is going to be somewhat beneficial. So I'm going to go over this. The first line is really just based on the definition of ki plus 1. And this is something that we talked about yesterday. So this is why I really like the summer session, because it's really kind of like day by day. So this way it's easier to retain what we have learned in a previous day. Especially if people review the content before class, they kind of go through a quick review of what we talked about last time, then it's even better. All right, so the first line is just by definition. And then to go from the first line to the second line, that is how the C function is defined for base 2. Okay, so for base 2, the C function is really just conjunction. So the C of xi, yi is really just xi and yi. And the C of qi, ki is really just qi and ki. And then this is a OR. Okay, it's not an actual addition, it is OR. So everything is in Boolean operators already. And we are just going to go through some derivation to make it, just change the way it is presented. I'll put it that way. And then qi is defined as the r of xi, yi, and this is how we define the r of xi, yi. We could have used exclusive OR, but I boil everything down to the 3 Boolean operators that we are familiar with, which is AND, NOT, and OR. So that's why I boil it down to like this one here. This is also something that we talked about yesterday. And then from here, okay, from here to here, that is the application of distribution. Boolean algebra allows distribution both ways, but this is the typical way that you are somewhat familiar with, because it's similar to distribution in normal algebra. And then from here to here, I just introduced this extra one, which is true. So xi and yi becomes xi and yi and true. That is not a problem, because true is the identity of conjunction. So you can always just add a and true or true and. It doesn't change the meaning of the expression. And this one is even more confusing, because the true is now becoming true or ki. Now if you have true to begin with, and you do a or with something, that doesn't change the true, because true or whatever is always true. So it would seem that I'm going in the opposite direction. In other words, it would seem that I'm making the expression more and more complicated unnecessarily. But we'll get to the point where we can start to do some simplification, and then we'll see that, oh, okay, so this is all going in one direction, seemingly making things worse, but it's just getting worse before it gets better. All right, so from here to here, it is distribution. So this one here is picking up the 1, and then this one here is picking up the ki. The rest are the same. And from here to here, now things start to get really weird, because you can see how I just replicated one of the conjunctions. Let me see which one I just replicated. I believe it is xi and yi and ki. It appears here's once, and now it is repeated over here. In Boolean algebra, that is perfectly okay, because if you have a particular expression, let's just call the expression w, okay? W or w is the same as w, right? So you can always have, and it also works out for conjunction. So you can always repeat the same term several times within, in this case, the overall or operation. And then from here to here, I group things. Okay, I put extra parentheses in. That is using the associative law of Boolean algebra. Kind of the same thing, very similar to the associative law in normal algebra. You just, because these are all OR operations, so however you want to group these subcomponents of the OR operation, does not change the outcome of the operations. From here to here is factoring, which is very similar to factoring in normal algebra. I just noticed that we have xi and ki in both of these terms. So the only terms that are different, which is yi in this case and not yi in the other case, they get extracted to become yi or not yi, which is the same thing that you would normally do with factoring in normal algebra. And the same thing over here, because I noticed that yi and ki is common for both of these terms. So the only terms that are different, which is xi in one, not xi in the other one, get extracted, and then the OR operation goes with those. And then from here to here is simplification, because yi or not yi is guaranteed to be true, because yi itself is Boolean. It can only be either true or false, but the other one is the opposite. So between these two, one has to be true, and because this is an OR operation, so that means the entire OR operation has got to be true as well. And the same concept applies here as well. And then we end up with xi and yi, or xi and ki, or yi and ki. And I do one last factoring, because both of these terms have ki as a component, and I just extract xi or yi to be ANDed with ki over here. So that's a really quick explanation of Boolean algebra with this derivation. And somebody is going to say, but Tech, that didn't solve the problem, because I can see that ki plus 1 is still dependent on ki. So the problem of carry ripple, which is basically the reliance of an earlier k term, to derive a later k term, that dependency is still here, because ki plus 1 still depends on ki. Yes, so that is true. I have not solved the problem yet. So at this point, I'm going to point out two definitions that many people will definitely not remember where they are in the notes. So it might be helpful for you to either highlight or write down on something. Okay, you can have your own document, you can have a physical notebook or whatever. Okay, whatever you do, make note of this. G of I is defined to be xi and yi, and then P of I is xi or yi. This is only defined once, and it is here. It is defined in a very obscure, short paragraph. Okay, but these two definitions are very, very important. Okay, so assuming that we define G of I as xi and yi, and we define P of I as xi or yi, then we can rewrite this expression as gi or pi and ki, because g of I is just xi and yi, and then p of I is just xi or yi. So at this point, someone's going to say, okay, all of this fancy stuff here is not solving the problem, because k of I plus 1 is still dependent on k of I. Okay, so but we did make the whole thing look simpler. Okay, that's one thing. It does look simpler. And what we will do now is to look at this definition of how we define k of I plus 1 using k of I. And we'll work this out and figure out what k1 is going to look like, what k2 is going to look like, what k3 is going to look like. And I can really just read the rest of the notes, but that's going to put you and myself to sleep. So I'm not going to do that. So instead, I'm going to use my tablet. So that way it is slightly more interactive. All right, so this is also a good point to kind of mention. I know many of you know this already, but I'm going to say it anyway. is when you are taking a class like this, it is a synchronous lecture and so on and so forth. It is probably not a very good idea to be multitasking. I'm not saying anyone is multitasking, but it is probably not a good idea to multitask because you should be you should be jotting down notes just like with a regular class, because remember what I just said, the definition of g of I and p of I is difficult to find. Okay, so you need to figure out a way so that you can quickly locate that particular definition. So Eric has asked a question. Can we do ki equals gi minus 1? Yes, you can do that. So you can basically shift the whole thing. I just like to look at the next column as I plus 1, but you can always refer to quote unquote the previous column, which is I minus 1. So either way works. It's kind of the same thing. Good deal. All right. So I'm going to jot this down, on my tablet. K of I plus 1 is defined to be g of I or p of I times or and k of I. There we go. Can we use that to determine k of I plus 1? Can we use what to determine k of I plus 1? Not sure what that is referring to, Eric. Yes. Well, that's the whole idea, right? Because the idea is g of I and p of I are very easy to compute because they are really just the conjunction and the disjunction of the bits coming from x, y, which are the binary numbers that we are adding. So k of I is the one that is difficult, okay? Because it is. So k of I plus 1 depends on k of I, which means if we are trying to figure out k of 64 with a 64-bit adder, then we need to first find out what is k of 63, which then depends on k of 62 and so on. All right. So
I mean, can
yeah, go ahead.
we? I turned my mic off because I got tired of typing. Um,
Yeah, go ahead.
can we substitute in the equation that I type? So g sub I minus one and so on. Substitute that into the k of I plus one
Yes,
equation.
that is exactly the technique that I'm going to use, but you have to start somewhere. So you're going to start with k of 1, depending on k of 0, and then you have k of 2, depending on k of 1. But then by that time, k of 1 is already quote unquote dissolved because it is now expressed only using k of 0 and then the p and the q terms. So I'm going to illustrate that.
Okay. I was
Um,
just curious if the substitution thing worked, if it
right.
was, I want to say linear, but I have no other word, so um, just curious.
Yeah, no problem. Yeah, and I have not started to share the tablet screen because I was copying this equation over to the tablet, so that's why it is not being shown yet. All right, so now it's time to show the tablet screen if I can find it. I have a lot of windows open. About I'm just counting here. I think I got about 26 windows on this in this particular desktop. So it does take a little bit of time to locate it. All right, there we go. So we have k of I plus 1, being g of I plus or p of I and k of I. So we're going to start with k0. So we'll say k0 is given. I'm using a thinner pen. Is that okay? Or do you guys want me to go back to the thicker pen? Or there's no preference?
Can you use
That one seems
thicker?
fine.
Sorry?
Can you use thicker?
Sure.
So better.
Yeah, if I use the thicker pen, it's just that I cannot it cannot be as concise because I can actually write really really small. Um, when I was a college student like you are, um, I used to buy wide rule binder paper, and you guys would go like, yeah, but everybody like college rule because they are finer and thinner. Well, that's because I can fit two lines in one line when I use the wide rule binder paper. And that's how I took notes when I was in college. I cannot do that when I'm using the thicker stroke, with this pen, but that's okay. So k of 0 is given, so we are not going to compute k of 0. So k of 1 is g of 0 or p of 0 and k of 0. So are we okay so far? Okay, because in this case I equals to 0, so that's why I plus 1 is 1, and then g of I is g of 0, p of I is p of 0, k of I is k of 0. So are we good here? This is kind of our base case. Then we move forward to the next one. Are we good?
Yep.
All right. So now we move up and we go like, what about k of 2? Well, that's easy peasy, right? So we have k of 2 being g of 1 or p of 1 and k of 1. And that's when I equals to 1. Then we go like, yeah, but that is still kind of, yeah, go ahead. Oh, I thought I heard a voice. Okay, never mind. All right, so in this case, it doesn't seem like we have solved the problem, but because we have already defined, we know how to compute k of 1 using g0, p0, k0, so we can do a substitution. So now we go like, oh, okay, so we can now rewrite this as g of 1 or p of 1, and k of 1 we'll use the expression that we have derived earlier, which is g of 0 or p of 0 and k of 0. Okay, so at this point you go like, yeah, we could do that, but it seems like you're not saving any time because these operations, this AND operation, this OR operation, still has to happen here. So we are not computing k of 2 any faster than before. Wait. Now we apply some magic, okay? Because we apply distribution. So now we have g of 1 or, and then we apply distribution. So we have p of 1 and g of 0. And then we have p of 1, p of 0, and k of 0. We apply the distribution. And somebody's going to say, but that doesn't help, okay? So this is really important, okay? Because I'm going to draw a circuit diagram to illustrate why it makes a difference between expression A and expression B. Okay, because expression A will take longer when it comes to logic gates to compute the result, and then expression B is going to be faster. So this is the part where you might want to jot down the time right now, which is 5:53. Okay, so you might want to jot down the time because that makes it easier for you to index back into the recording so you can watch this part again if you need to watch it again. All right, so we're going to look at circuit A, okay, or the circuit to implement the expressions in expression A. So we have to start from inside the parentheses, because all that stuff needs to be computed first. So we have P0, K0 going into an AND gate like that. So what comes out is going to be the conjunction between K0 and P0. And now we have G0 going into a OR gate with the result of the AND, like so. So now we have the result inside the parentheses, and then we have P1, okay, and all of this is going into an AND gate. And then we have G1 going into an OR gate. So we have G of 1 going to the next level, which is going to be an OR gate, like that. All right. So we want to look at how much time it's going to take in order for the output, which is right here, to settle down, because there's always an output. The question is the output correct? Okay, that's the only question. So we want to figure out how much time does it take for the last OR gate to output the correct result based on the P terms and the G terms. So we are not too concerned about the time to compute the P terms and the G terms because they are, one is the conjunction of the XY and the other one is the disjunction of the XY. So that is really not so much of a concern. So now we basically have to say, because with each gate there is a propagational delay. So there's a certain amount of time here so that when the input of a gate changes, there's a certain delay before the output is updated because of the change of the input. That is called a propagation delay. So every single gate, AND gate, OR gate, exclusive OR gate, NOT gate, and so on, every single gate has a propagational delay. So now, after this output is correct, then we can compute this result over here. So now we have a second propagational delay, and then when this output is done, then the output of this AND gate can be trusted, and there's also a propagational delay to compute that. And when the output here has settled, is correct, then there's also propagational delay from here to here. So now we can see that with expression A, there are 4 propagational delays. Okay, and I'm making the assumption that a conjunction and a disjunction has the same propagational delay, which is okay. Okay, that is not a big deal. Okay, because we are just counting the number of gate delays at this point. What about B? Option B is a little bit different because G1 is basically all by itself, and then we have P1 G0 going into an AND gate like this, and then we have P1 P0 K0 going into another AND gate. So we have P1 P0 K0 going into another AND gate. And guess what? Both of these AND gates can compute at the same time. So now the output of the 2 AND gates and G of 1 would go into the final OR gate like this, and then we have the final answer. So because the 2 gates here can compute at the same time, so they're going to use only one propagational delay because they are computing at the same time. Okay, from the moment that we have the P and the G bits ready, then there's only one single propagational delay for both of the AND gates because they are computing in parallel. So when the output of the 2 AND gates have settled, then we have a second propagational delay because of the OR gate. So we only have 2 propagational delays instead of 4 propagational delay of expression A. So I'm going to kind of slow down here a little bit to make sure that everybody can see the difference between expression A, which is this one here, and expression B, which is after we apply distribution. Are there any questions about how these two differ? Okay, no questions. All right. So if there are no questions, we're gonna go through this, one more time and derive k of 3. So k of 3, according to this particular equation, is g of 2 or p of 2 and k of 2. Okay, this is when I equals to 2. But since we already know how k2 can expand, so now it becomes g of 2 or p of 2, and then we substitute. Okay, we substitute the expanded version of k of 2, which is this mess over here. So I'm going to write it here, g of 1 or p of 1, g of 0, or p of 1, p of 0, and k of 0. So once again, in this particular format, is not optimized. Okay, it's going to take some extra time, or to be more exact, it's going to take 4 propagational delays. So we are going to make it more optimized by using the distribution rule again. So now we have P2 G1 or P1 G0. Oh, okay, I got it wrong. And then P2 P1 and G0. And then we have a or P2 P1 P0 K0 over here. So we finally have, okay, let me just double check because it doesn't, no, it's right. Okay. This is a G, by the way. Penmanship is kind of bad. This is a P, so that's why these two are different. So now we look at this particular equation. We'll call this one expression C. Can anyone tell me how many propagational delays expression C is going to take when we implement it using logic gates? Very good. Okay, so we got, Paul and Fulin are both correct. It's going to take up only 2 propagational delay. This is the magic of carry look ahead adding. Okay, because the propagational delay of computing any k term is only 2 propagational delays. It's constant. Okay, the key is it is constant. It would take the same amount of time to derive k64 in a 64-bit adder as it would take to derive k of 1, k of 2, k of 3, and so on. All right, so Fulin has a question. Does the order matter? Like P2, P1 is the same as P1, P2. That you are correct. The order does not matter. The order doesn't matter because the operator itself, conjunction, is commutative. So that's why the order does not really matter. Alrighty. So this is it. Okay, this really kind of illustrates why or the mechanism how carry look ahead works. Okay, this is the most important part. So that's why I said a little bit early you might want to time mark the lecture at this point, which was 5:53. Okay, see, I still remember that time mark. Because this is really kind of the important part of carry look ahead adding. And this summer session is the first time that I illustrate the whole point using the tablet like the way it is, instead of just relying on the notes. So you guys are the guinea pigs of the new way of explaining the same concept. Cool. Do we have any questions? Okay. But you might have noticed, okay, so even though we solved the problem of not having the ki plus 1 term to linearly depend on k of I and so on, so we have solved that problem. But it seems like k1, k2, and k3, they are not really quite similar anymore. Okay, because k1 looks like this, which is really simple. K2 is a little bit more complicated like this. K3 is even more complicated. And using just intuition, you can probably guess that K4 is going to be just one step more complicated than this. There will be one more term in the disjunction, and then other than the first term, okay, we'll have one extra term that has 5 things, one conjunctive term that has 5 things in it. Okay, so now the question is, how do we generalize this, right? Because if you're working for Intel, or if you're working for a company where they want you to design a carry look ahead adder that is 64-bit wide, you're not going to do this by hand. Okay, there's I mean, I wouldn't do it by hand if I need to derive k of 64. So now the question is, how do you make it? How do you write out, k of 64. That is what this thing is for. Okay, so I know that there are some notations here that you are not familiar with, so I'm going to go explain what those notations are. So we'll start with this kind of inverted V, big inverted V symbol. It is almost the same. It's basically a series. It is the conjunction of a series. Okay, that's the best way to describe it. It is the conjunction of a series where the indexing is based on j. It starts with I plus 1, it ends at n, and then each term that we are ANDing in the conjunction is p of j. That is what this portion is meaning. So the big V symbol is doing the OR. So the big V is the disjunction of a series. The index of each item in the series is controlled by I in this case, which starts with the value of 0, ends with the value of n, and then each item that we are ORing is this expression here. So as you can probably imagine, this is really going to be a little bit complicated, okay? So you're going to use a loop to do it, okay? All right, so does everybody understand the notation? Or do you guys want me to kind of talk more about it?
I would like you to talk about it.
Sorry?
I would like you to talk more about it.
All right, absolutely. So
Yeah, I think so too. I'm not sure what disjunction and conjunction are. I missed that part.
a conjunction is an AND, a disjunction is a OR.
Oh, okay. Never mind. I got it.
Just fancy terms. I'd like to use the term conjunction, a series of conjunction, a conjunction of a series, as well as a disjunction of a series, because the word and or are too common. Sometimes I have to use it inside the sentence itself, and then when I need to refer to and or as the actual operator that I want to refer to, it gets confusing. But if I say, this is a disjunction of a series, then it becomes clear that when I refer to disjunction, I'm referring to it as the operator, and I'm not using it in the colloquial sense of or. So that makes it kind of easier to differentiate the terms. All right, in calculus, series implies summation of a sequence. So that would be, well, a series is really just an expansion, or does it always imply summation? What about n times n minus 1 times n minus 2 times n minus 3 factorial? I think a series is really just a bunch of values where they are indexed. Yeah, but it's a product of a bunch of stuff. Okay, just hold on a second. I'm gonna look up on the side. I do not mean to be nitpicky about terms, but I do want to make sure that I use the right term.
No, I think I'm the one being nitpicky here, but I feel for calculus students and when we talk about series and sequences,
Uh-huh.
it's very easy for people to get confused between the two. And
Mm.
sequence always implies like an ordered set essentially,
Mm-hmm.
which may be infinite, whereas series does always imply the operation of summation.
Yeah, I'm looking at Wikipedia, and it does specify that in a series, it is usually using the summation or the sigma notation. So that is by the definition of the sigma notation, it is a summation of terms. Okay. I just have to think about how to explain this. So this is a conjunction of terms. This is a disjunction of terms where each term looks like g of I, and the conjunction of terms of a bunch of p of j's. All right.
Yeah, I mean, you could say an indexed collection of terms if you want to avoid sequence or series altogether, but
Okay. That's a good alternative. Yeah, that's a good way to describe it. This happens to me a lot. I have a concept and then I just have problems, putting it into words. Because I guess when I think, I don't use words. Weird problem on my side. Okay. So, but the best way to explain this is to show you some code. Okay, so I'm going to show you actual code that works, that will kind of spew out, what k of n plus 1 is going to look like. Okay, so I think this is going to be cool. This is going to be cool. And also, this is the first time ever that I do it this way in the class. So even though I teach the same content every single semester, I do change the way that I teach the content. Um, just to, sometimes I just figure out, oh, this may be a good idea. Sometimes it does not turn out to be a good idea. Other times it does. All right, so I'm going to use look ahead, and this is going to be in JavaScript. And when you use JavaScript outside of the context of a browser, it is usually known as Node. JavaScript is actually a subset of ECMAScript. That's the formal term of that quote-unquote programming language. So ECMA, E-C-M-A, is the name. If you want to look it up, here it is, ECMAScript. There we go. So ECMAScript is the scripting language that forms the basis of JavaScript. There we go. Little fun facts. All right, so I'm gonna write the code and do it again. So this way, I always use strict. So this way I cannot use variables unless they are declared. And then I'm gonna define a function, which is going to figure out k of a particular bit. So I'm gonna say k of let's make it n. All right. So the way it's going to do that I'm going to do this. Okay, so I'm looking at this, and I think I'm not gonna make it too fancy, because I could have used iterators, and then and a whole bunch of other things. I'm just gonna use regular loops. Okay, so instead of using iterators, which will make the code a little bit harder to understand. So I'm going to use loops. Okay, so in the loops, I have I. Okay, so we're going to say I goes from 0, and then the last condition that still needs to be true is when I does equal to n. So instead of I being less than n, I is less than or equal to n to stay in the loop, because I is supposed to get to the value of n in this case. All right. And then plus plus I. So for loop is for loop, okay, in JavaScript or in C or C++. So the only difference is there's no type, I is not int. I just use let so that we understand this variable is visible only within this particular block. We also need to keep track of the actual string that we are generating. So, and also things that we are ORing, things that we are ANDing, and so on. So we are generating things to be ORed. So we'll say let OR terms, be an empty array at this point. And then from here, we have to look at, okay, now it becomes g of I and the rest. Okay, so I'm going to compute the rest here, which is using a embedded loop. So now we have for let j equals to 0, j, I take it back because j is supposed to start with I plus 1, and j, the last value of j is supposed to end with n, so j has to be less than or equal to n, and then plus plus j. There we go. So here's our embedded loop to implement the nested conjunction of pj terms. And then before that, we're gonna have to put in let end terms equals to an empty array, and then from here we just have to say, oh, from here on it's pretty easy because the term that we want to put into the conjunction is just p of j. Okay, so we will say and terms dot push backtick p of j. So JavaScript is kind of neat because it allows you to use the backtick notation. For those of you who know CISP310, it's kind of like that, except you don't need to actually pass the value of j. It expands within the string as long as you use the dollar brace, blah blah blah, and brace notation. So it's really kind of neat. All right. So by the time I exit the loop, I would have all the conjunctive terms using this loop over here. We just have to also push g of I. So we're going to say this time and terms dot. This one is going to be unshifted. So push is always appending at the end of an array, whereas unshift is putting it at the beginning of the array and then shifting everything else down, by one element. Okay, so I'm going to use unshift because I want it to look in the right order, even though conjunction is commutative and the ordering does not matter. I still want it to look consistent with the notes. Okay, so I'm going to put an unshift here, and this is going to be g of I. So g is literal, and then I is going to be expanded from the loop control element. So there we go. And then after that, we have all the AND terms done. So we'll go ahead and create the string for the AND term to become a single item of the OR terms. So now we have OR terms dot push, and it's going to be AND terms dot join, and we don't, using the new notation, the AND terms, when we use AND or conjunction, there's no actual operator between the terms that we are ANDing together. So that's why I'm using just an empty string for the join operation. So for those of you who do not know what join is doing, it's taking all of the elements of an array and combining all of those into a single string, and then the separator between the items of the array is whatever you pass as a parameter to join, and in this case it is an empty string, so they will just be bunched up together, much like what we have seen already in the notes. All right, so when this loop is done, we would have done this side already, so we just have to deal with the other side, which is k0 and this term here. So we'll go ahead and do that part. So we're going to say let, I'm just thinking, do we need to use another one? Probably yes. So we need another AND term here. Okay, so this AND term does not have anything to do with this AND term because the scope of this AND term is only within these braces. And then this AND term has a scope of between these braces, but only after the point where I use the let syntax. And then we have a loop again. So this time I use I again, because I is already done. Okay, this loop here is already done, so I can use I again. And besides, I has a scope of within the for statements, so I is not visible. This particular I here is not visible even at this point. So because they're not within the same scope. So yeah, go ahead.
In the notes, you have the formula for kn plus 1. So I think we should go up to I equals n minus 1. Isn't that?
Oh, right. You're correct. You're right
And
about
J.
that. Not the best way to do it, but it fixes all of the references to and at the same time. Okay, so we have p of I, so we're going to say and term dot push P of, oops, I, like that. And there we go. So by the time this loop is done, it would have the conjunction of P0 all the way to up to Pn. And then in the notation that I use, K of 0 is appended at the very end. So I'm going to append it this time, which is another push. So K0 is going to be pushed at the very end. And that's going to be my last term of conjunction. And that's going to be ORed with everything else. So now I can use OR term dot push and term dot join empty string, like so. So at this point I have everything. I have all of the terms to be ORed together. So the return value is going to be OR terms. Okay, I use plurals sometime and not plural terms, some other times. There we go. Alright, so return OR terms dot join, and we do want to use a plus symbol to separate the terms that we are ORing together. So that's it. That's the function, and we are going to give it a try. I cannot remember how to refer to parameters, so I'm going to look it up here. Node argv. Okay, it's in the environment of process. Okay, so is process. Okay, looks like process is going to be by default over there. Okay, so we can now call the function, which is k, and then we'll pass process.argv, and that is supposed to be an array. I'm just double checking. Yeah, that should be an array. Slides 2, because the first two items are not useful, and we're passing the first item beyond the first two items, which is the third item. I suppose we can just use bracket 2 instead of this method of doing it. So we'll give it a try, and this is all going to be done, and there will be no output. So I'm going to put in console.log, so it will print something on the screen. All right, and chmod. I have to change the permission so I can actually run it. If you're using DOS or Windows, there's no such thing. But when you're using Linux, you have to change the permission so that you can actually run it. Or you can say node and then la.js and then whatever the parameter is. But this way, I can just run it. And we want to try it with 1 first. Okay. And of course, it doesn't work the first time because I did not consistently use the plural version of the terms. Okay, so we'll look for and term and not s right after. So this way I'm locating, every single one of the mistakes. Okay, so this was the only one left. There we go. All right, cool. Let's try 2. Oh, that doesn't look good, but it does work. And we'll try 3. It has to do with the loop. Okay, so I'll explain it. Okay, it doesn't look the same, right? Compared to the notes. So if you go back to the notes here, k of 3 is g of 2 plus p2 g1 and so on, and that has to do with the loop is appending things to the end. So I can change the way I put the items into the loop. So instead of a push here, I can just unshift. There we go. That should fix that problem. Oh, okay, never mind. It's the other one. So that unshift should be the same as as before. Nope, that one should be unshift. This one should be unshift too. There we go. There we go. Okay. Yay! Now it looks good. Yes, I just spent the last 2 minutes, fixing something that really does not need to be fixed because in a conjunction, things are commutative, so ordering really does not matter. But it just bothers me when the output of the program does not match what I have written here. Oh, it still doesn't match because the G term is unshifted into the P terms. Okay, let me fix that one more time. Because the G term is supposed to be after, so this is going to be a push here. There we go. Now it looks good. All right. So after all of this, does that help explain this notation? Because all the program did was to implement this notation. Is that helping or is it hurting? Because sometimes when I try to explain something in a better way, it doesn't work. Does it work this time?
It is making some sense, but I would like you to explain what is unshift, if you don't mind me asking.
Unshift. Okay, there. Okay, let me point you to a resource. Okay, so if you just look up JavaScript array unshift, that will bring you to the documentation of unshift. So unshift adds one or more elements to the beginning of an array and returns the new length of the array. So we are not really using the return value. We are basically just saying we are always adding items to the beginning of the array and then shifting the existing elements down the array when we are using unshift. Push on the other hand would append the new items at the very end of the array. So one would insert at the beginning, the other one appends to the end. Does that help?
Yes. Thank you.
All right, cool. So I hope this program does help, to illustrate, the what that function is doing, because all it does is really just a bunch of loops and, ending and oring, the terms that we generate when we go through the iterations of the loop. And of course, I have to do this, okay? What about K64? What is that going to look like? I have to do this. I'm sorry. I have to do it because I have to show you why it doesn't make sense to do this manually. All right, so the alarm of my Fitbit just went off, so it's time to take a roll. All right. All right, so it's not active yet. I have to release it, and I'll give you guys up to 6:35 to do it. But I'll show you the answer first. Okay, I'm gonna show you the answer first, and then when I release it or publish it, you guys can go ahead and answer the question. Because we are talking about carry look ahead, so the word that I have chosen is headlight. So once again, headlight is the word for row taking today. Let me type it in. I do not know yet. Okay, it's for most people it wasn't missing. And then we'll put a date here. Today is June 10th, and I'll make it due at June 10th. We'll make it due at 6:35 p.m. and then save and publish. What do you mean by there were two?
By looking at the dashboard, there's one I guess quiz because
Oh,
these
okay.
role taking quizzes are like, both of them have the same name, but today I noticed there's like one missing for whatever reason. I don't remember there being two yesterday.
It's same for me.
I have
I
the
just
same
got
problem. Same for
If
prerequisite check also.
Yes. Here.
so,
no,
it,
just
it
roll
appeared
take.
twice.
Yeah.
Yes.
Oh yeah, prerequisite check also came up yesterday for whatever reason. It says it's missing, even though it's not.
Does it report it's missing in your gradebook?
Let me see.
Yeah, yes, that's what we're looking at on the grade page.
Yeah.
It's showing missing twice.
Yeah.
All right. Well, go ahead and use Canvas to contact me. I specifically want to use Canvas because that way I can more easily look up your entry.
All right.
Thank you. Because I looked at my gradebook from my side, and most people were not didn't have it missing. There were like maybe 2 or 3 people who actually did not participate in the road taking activity yesterday, and it only showed that those people did not participate, but the rest of the class did.
So do you want any of us who it shows missing on Canvas for to contact you, or do you think it's fine if it didn't show missing on your end?
Go ahead and contact me. Oh, okay. So the quiz was locked. Okay.
I submitted. It's unlocked.
Yeah. There were 2 0609 road taking because oh, okay, I know why. I know what it is. Because I made a copy and I could not find where it made the copy. So it made a copy somewhere that I could not see in the modules. Oh, okay, it appeared here now. Okay. I'm gonna get rid of the second one. Let me just double check to make sure this is actually the second one. Yep, this is going to be the second one. I'll double check.
Professor, I have a question.
Yeah.
For my pre-quiz, it said is missing as well, but you have gave me 1 out of 1 at the first day. Is that will cause an issue or no?
I do not know why it is reporting it is missing. So I'll take a look at that after class.
Yeah, for sure. Like, I mean, for sure, I know myself that I took, the pre-quiz before that class. So
I think it doesn't matter as long as you have 1, like 1 out of 1. Then
Yeah.
I guess that's all that matters.
Oh, okay. I just want to make sure because since we start talking about a lot of stuff, and especially it's missing, I just want to confirm. I don't want to get dropped. That's why.
Yeah.
Yeah.
Thank you.
Yep. All right. So are we good with today's road taking? Is anyone still working on it?
His days seem to work fine.
Okay. All right. Okay. So if that is okay, I'm just tracking the almost hit a deer. Then you're gonna have dinner for the rest of the month. Yeah, you want to be in a rear-wheel drive vehicle like a Porsche. But if you were to hit a deer with a Porsche, I think the deer would just kind of fly up and land behind the vehicle. Because the Porsche looks like a little shuffle and is too low to actually hit the vitals of a deer. Anyway, so we are that's right. So we are pretty much done with binary addition. So I want to see if anyone has any questions about the binary addition module.
So the code that you wrote was not in C++. That made it difficult for people that have never coded outside C++, like myself.
Mm-hmm.
So not now, obviously, but later on, could we have a version of that code just for our benefit?
Mm.
Is
That
that too
is a
much to ask for?
okay. So it depends on the long term and the short term benefit, because in the long term, learning JavaScript is probably the better way to do it. In the short run, yes, I think C++ may have array. If you use the template class array, it might have shift and unshift and push and all of those methods as well. So I can look up C++ array shift unshift push. Okay, we got Perl, we got C++. This is in the forum, and it has Q. When you have use a Q, it has push and pop. And let me see. Nope, does not have shift and unshift. So those seem to be native to JavaScript, but not so much with C++.
Ah,
But all they do is one is inserting items at the beginning, and the other one is appending items to the end. That's the only
sure.
difference. So
It,
yeah.
the algorithm of it makes sense. Like I get it,
Mhm.
but as far as like checking work for when we do things beyond like I equals 4,
Mhm.
that would be, I'm guessing, beneficial. I don't
Yeah.
know what the course entails, but
Well, the only difference, is the terms is going to be quote unquote out of order, but they would not be incorrect. They would just be in out of order. Instead of having this nice neat order, they would just be kind of like, the K, it may appear at the beginning, and then you might have, P. I mean, this is out of yeah, this is out of order too. Okay, the last term, because in my notes it starts with P3 and then P2 and then P1 and then P0. That's the only difference between shift and between unshift and push is, the ordering. And because conjunction is commutative, it really doesn't change the correctness of the output.
right. Makes sense.
Yep.
Okay.
Alrighty. Yeah, it's not a very it's not as simple to do this in C and C++, just because there a lot of the native methods of array, which are really super duper useful, are in JavaScript, but they are not in C or C++, or even Java for that matter. Okay, so any other questions about this particular module, about binary addition? Okay, I can hear the crickets. Oh, solution for the last lab. Sure, absolutely. Let's do that. So solution of the last lab, which is base conversion? Is that what Boolean is referring to? Oh, okay. Well, it's not going to be the solution for you. So what I can do is to release the solution for you, because there's a setting here that allows me to do that. Alright, so let students see their quiz responses. And let's see, where does it say see the correct answer? There we go. And I think if I click save, you should be able to see the correct answer. But I think what Fooling wants to do is for me to actually illustrate how to do it. So let me do that. All right, so question number 1, what is the digit for the first place? Yeah, I cannot, change the grammar because when I use a equation to generate alternatives for in Canvas, it only gives me so much wiggle room when it comes to which part of the question can be customized. So I can't really change this part here. So first is really kind of like digit 1 of the base 4 representation of the value in as 169 in base 10. Okay, there we go. So we have to use the okay, now would be a good time to pull my tablet out. There we go. The tablet is sleeping at this point. Okay. All right, so new page. So we are going to use 169, which is a value, divided by 4 to the power of 1, because that is the digit position. Take the floor of that and then mod it with 4. That's how we figure out digit 1 of the base 4 representation of the quantity that we know as 169. So we'll do some quick math on the side. 169 divided by 4 is 42.25. Let me double check. 4 times 4 is 16. 2 times 4 is 8 with 1 as a remainder. 1 divided by 4 is 0.25. So that seemed to be right. So now we have 42, because that's the floor of 42.25, mod 4. And that's going to be 2. Alright, so we'll put in the answer. And 2 for this one. So any questions about how I answered the question? Okay, no. Okay, we'll move forward to the next one, which is what is the base 10 representation of the value represented by the following base 7 number? So 310 is a base 7 number. And once again, we go to the tablet. We have 310 as a base 7 number, which translates to 3 times 7 squared plus 1 times 7 to the power of 1 plus 0 times 7 to the power of 0. So that boils down to 3 times 49 plus 1 times 7. And 3 times 49 is 147 plus 7. So we have 154. Okay. 154. Next. Alright, so this time it is also the digit 1 of the base 4 representation of what we know as 137. Alright, so let's go ahead and do that. So 137 divided by 4 to the power of 1. Take the floor of that and then do a mod 4. So 137 divided by 4 is 3. And then we have a 4 here. 34.25. So it's 34 mod 4, which is 2. Just so happens to be the same digit as the other question. And then the last one is given a base 7 number converted into base 10 again. This time it is 431 in base 7. So 431 in base 7. So I'm going to shortcut it this time. This is 4 times 49 plus 3 times 7 plus 1. So the first part is 200 minus 4, which is 196, plus 21 plus 1. And that is, okay, we end up with an 8, and then a 1, and then a 2. So it's 218. As you can see, my mental math is not really fast. Not fast by any standard. So I think that is right. Okay, let me just double check. Yeah, looks right. All
Can we
right.
have an example of converting a base 7 number to base 4?
Okay, so let's do that. Let me submit first and see if I got it right. Let's see. There we go. Okay, that's good. That's good. That's good. That's good. Okay, well, okay. So the question was, can we convert from base 7 to base 4 without going through base 10? I would assume that's the implication. Is that right?
Yes.
Okay.
Yes, that's correct. Because that's the way that I would do it. And
So base
I'm not
4.
smart as
Okay. We'll give it a try. Okay. So base 4 to base 7 or the other way around?
either is fine.
Okay, base 4 to base 7. Okay, so we'll give it a try. Okay, so let's say we have 2, 3, 0, 1 in base 4, and we want to find out, what does this look like as a base 7 number. Okay, so it still boils down to the same thing, because we need to figure out how many. We need to figure out, what is the most significant digit that we have to deal with, and before we do that, we have to figure out the actual value represented by the base 4 number. And because we have to do division, so in order to do division, we have to figure it out. Now, you can directly do division in a different base, so we'll go ahead and do a division in base 4. So we have 2, 3, 0, 1, and we divide it by 7. Okay, so now the question is, can we do this? The answer is no, because there's no 7 in base 4. The quantity that we know as 7 is not a single digit. Okay, it is actually represented as 1, 3 in base 4, because the 1 tells us we have 1 of 4, and then the 3 tells us that we have 3 of 1. 1 is 4 to the power of 0. Okay, so we have 1 of 4 to the power of 1, and then 3 of 4 to the power of 0. So when we do division, we have to make sure that everything is expressed in the same base. Okay, all right, so now we look at this and go like, okay, there's a 0 here, and I think it is safe to assume there's only 1, 1, 3 in 2, 3. So now we do a subtraction in base 4. Okay, this is a base 4 subtraction. We have a 3 minus 3 is always a 0, 2 minus 1 is a 1, and then we put 1, 0 over here. So this is where things get a little bit awkward, because 1, 0, 0 in base 4, now we have to figure out how many 1, 3s we have in 1, 0, 0 in base 4. That is not easy, because I'm gonna guess 3, but I could be wrong, because our multiplication table that we have memorized in our head doesn't work now. So we're gonna have to do a quick conversion here. So I am suspecting a 3, because if you add 1 to this, you get a 2, 0. Oh, maybe not 3, maybe just 2. We'll try it. So we'll try a 2 first. And 2 times 3 is not a 6, right? Because we're talking about base 4. So 2 times 3 is actually 2 with a carry of 1. So it's a 2 with a carry of 1. And then we have 2 times 1, which is still a 2. And we have a 3 here. And then you do the subtraction. 0 minus 2 is not 8, because we're dealing with base 4. So 0 minus 2 is actually 2 with a borrow. You can probably see why this is going to be a little bit tricky. So we have 0 minus 3, which is 1 with a borrow, and then 1 minus 1 is a 0. So we only have 2 left. So 2 turned out to be the right choice. So we have 2, 1. And I am suspecting there's only 1 of 1, 3 in 2, 1 in base 4. So we will give it a try. So we have 1 minus 3. 1 minus 3 is not In base 10, what is it? In base 10, it is 8 with a borrow. But in base 4, it is not. Okay, in base 4, 1 minus 3 is a 2 with a borrow. So now we have 2 minus 1, which is 1. 1 minus the borrow is 0. So we have a remainder of 2. So that tells us in the base 7 representation, 2 is the least significant digit. This is digit 0. So we know digit 0 in base 7 is going to be a 2. And then in order to figure out digit 1, we have to find the remainder of 1, 2, 1 in base 4 divided by 1, 3 in base 4. I'm just looking at the time. Okay, we are running out of time, but I am going to do this because I'm a little obsessed with this now.
So pretty much it's faster and safer to convert it to base 10 and then into base 7.
Yes, simply because we have memorized the multiplication table in base 10 already, and that's just, it just makes it easier, right? You know, it's once again, you know, okay, I shouldn't say once again because I said this last semester, but I have not said it in this class yet. The reason why it's faster to convert it into base 10 first is because we have been poisoned by base 10 ever since we went to school.
I don't know. It worked out pretty well all my life, so.
Yeah, well, you know, it's well, as they say, if you have a hammer, right? If all you have is a hammer, you just keep pounding, and you know, once after a while, you know, you feel comfortable. This looks like a nail, only it has got some, you know, really strange things, you know, called thread on it, but it does look like a nail. I'm just gonna use a hammer, you know, and it seems to work too.
That's a slightly difficult nail.
Yes, yes. But you can probably see that this will also work because, you know, 1, 2, 1 divided by 1, 3, some rules are always going to work regardless of the base. So the only thing is, you know, is it going to be a 3 or a 2 here? That's the only one that I cannot be sure. So if I put a 3 here, 3 times 3 is not 9. It is, let's see, it's going to be a 1 with a carry of 2. Okay, so it's going to be a 1 with a carry of 2. And then 3 times 1 is a 3. And then 2, oh, okay, so it does evenly divide, actually. So 3 times 1, 3 is indeed 1, 2, 1 in base 4. So now we know D1 is a 0. And then D2 is going to be a 3. In other words, in base 7, 302 in base 7 should be the same thing as 2301 in base 4.
And the question I have regarding this is, for humans, it's really fast for us to convert to base 10, but for a machine, is it faster for it to convert between lower bases rather than higher, or?
Okay, so for a machine, everything is in base 2 already. Okay, you know, when you look at a C program, you get to see, oh, but this is in base 10, right? No, the compiler converts everything to base 2 before it is stored in variables. So everything is already in base 2 by the time your program runs. It is just that when you look at the source code, that it looks like it is actually in base 10, but it's never actually stored in base 10. But I'm still obsessed. Okay, let me release the lab first, just so that, you know, people who are cannot stand my obsession can move on and do the lab and just turn me off, you know, from the live share or the screen share. Because I can understand that. I can understand why people may say, but Tack, this is way beyond what we need to know. But I think it is kind of interesting. So that was a good question. I like that question.
And a follow-up question, if you don't mind me asking.
Sorry?
Follow-up question, if you don't. Yeah.
Yeah, go ahead.
If the compiler is going to convert it to base 2, if you programmed in base 2, would it still compile it into base 2, or would it just use it as is?
Well, okay, first of all, C does not have a way to enter a number in base 2. It just is not an option. Okay, so the multi is the key. Okay, multi is the passcode of tonight's lab. And I'm going to specify the due date. It's going to be today, which is June 10th. And I'll make it 8:25 p.m. Instead of the usual 8:20 because of my obsession with the question I'm still answering right now. So we'll make it 8:25 and save and publish. There we go. All right, so for people who really just kind of do the lab and get out of the class, go ahead and mute me, from Discord. But I'm gonna move on and continue to work with that. Oh, okay, so I made a mistake somewhere. Base change from 4 to 7 to 301 is supposed to be 342 in base 7, so I made a mistake somewhere. I got the 2, but the 4 is the problem. Oh, I know why, because it's a 1 0. So when I got to D1, okay, which is okay, I cannot remember which one got me that's 0. It's the remainder of 0. Okay, it's the remainder. All right, so that means this math was not correct. All right, 3 times 3 is 2 1 in base 4, and then 2 minus 3. Okay, 2 minus 3 is a, let's see, it's a 3, and then 3 minus 2 is a 1. So we do not have a remainder of 0. Okay, so that's why it's wrong. So we have 1 minus 1, that is a 0. And then 2 minus 3 in base 4 is a 3. 3 minus the borrow of 2 is a 1. So we do have a remainder of 1 0. And that's why we are supposed to have 1 0 here. This is 1 0 in base 4, which is 4 in base 7. So that's where I messed up. Very good, Paul. Good job finding the tool to do the conversion. But I did make a mistake. I didn't check my math in base 4 subtraction. So that's a good thing.
In the notes, you recommended that we program this, so I took you up on your suggestion.
Nice, very good. What language did you use to do it?
That's Julia.
Julia. Okay, I'm not familiar with Julia. Okay, let me look it up. Julia programming language. Oh, interesting. It has. So it looks like it is it borrows elements from a lot of languages. Is that kind of what it is?
Yeah, it's a lot like Python and some of the array stuff in Python.
Okay.
But it's meant to kind of solve the two-language problem where you have prototyping that's done in like a scripting language, but then performance code that's done in C or C++. The idea is to try to push those things a little bit closer together so that you can get really, really high performance scientific computing out of something that that kind of reads like a scripting language.
Interesting. Okay. I might take a look at this because I do most of my non-performance sensitive coding in Node, just because Node has it's just really convenient to do a lot of things. So if Julia has elements from Python, that means it probably has similar features compared to JavaScript. So arrays probably have the native methods of shift, unshift, push, and pop. Okay.
Yeah, what I saw is push and then push first, which is very intuitive.
Okay.
Actually, I did want to ask you just kind of about those of us who are on the wait list. Are we? Is this the end of the road for us, or do you have an idea?
Well, let me take a look at the roster first. I cannot show the roster on the screen share, but I can. Let me take a quick look. Oh, okay.
Professor,
Mm-hmm.
in the lab, Canvas appears to drop all of the leading zeros.
Yeah, that's fine.
Okay, cool. Just making
Mm-hmm. Yeah, the leading zeros is not going to affect the correctness of the answer. All right. So it looks like, I think I'm just going to go add everybody to the class. So if you have been attending classes consistently, um, and you're on waitlist, I'll give you a permission number so you can use it before tomorrow, so you can just go ahead and add yourself to the class. And also, by the way, if you're on waitlist, you have to drop yourself from the class first before you can use the permission number. So keep that in mind. I'll be if I don't have any questions to answer on Discord, I'm going to start to distribute the permission numbers. All right. Is that a satisfactory answer? Okay, I'm looking at the text channel. Looks like it is satisfactory. All right, I'm gonna turn off the voice channel now, and then focus on distributing the permission numbers.